We're comparing two ways to estimate covariance: the standard sample covariance and the ledoitwolf estimator. I'll explain their differences and when you'd use one over the other. It's like choosing between a simple, quick calculation versus a more sophisticated method that's less prone to errors. We're working with a dataset that has 100 data points, each described by 5 characteristics or features. This specific number is important because the ratio of samples to features influences which covariance estimation method is best. Imagine analyzing how height, weight, age, blood pressure, and cholesterol levels relate in a group of 100 people. Sklearn is a popular Python library for machine learning. The ledoitwolf function within it calculates the ledoitwolf covariance estimate. It's a specific tool for handling a problem inherent in some covariance calculations. The ledoitwolf estimator guarantees a positive semi-definite result. This is a crucial property for many statistical analyses. Think of it as ensuring the resulting covariance matrix is mathematically well-behaved. This is false. I will explain why. The ledoitwolf estimator is actually more computationally expensive than the straightforward sample covariance. It involves additional calculations for shrinkage. The ledoitwolf method truly shines when the number of features is much larger than the number of samples, high dimensionality. This is where the regular sample covariance often falters, whereas ledoitwolf provides a more robust estimate. It's like navigating a complex terrain with a sophisticated tool versus a basic one. This is false. The ledoitwolf estimator doesn't make assumptions about how the data is distributed, e.g., whether it follows a normal distribution or not. It works with the data as is, making it a versatile and reliable technique in various situations. I see the sample covariance matrix as a straightforward way to estimate how features relate in your dataset. It's a simple calculation, but it can be unreliable when you have many more features than samples. Think of it like trying to build a really tall tower with a tiny base. It's unstable. It can even become singular, non-invertible, which makes it hard to use in some analyses. The ledoitwolf estimator is a smarter way to estimate covariance, especially in situations where the sample covariance falters. I think of it like adding support beams to that wobbly tower. It shrinks the sample covariance towards a more stable target, ensuring it's always positive semi-definite, meaning it's mathematically well-behaved. The amount of shrinkage is automatically determined using the dataset information, making it a data-driven solution. The key difference lies in how they handle high-dimensional data. I'd say the sample covariance is like a simple, quick calculation that may not be entirely accurate. The ledoitwolf estimator is more computationally involved, but it offers increased stability and reliability, particularly crucial when dealing with high dimensionality, where the sample covariance can yield very unreliable results. I'm analyzing a dataset using the ledoitwolf covariance estimator, a technique from the Sklearn library. This estimator helps us understand the relationships between different features in the dataset. I have 100 data points, each described by 5 different characteristics or features. Think of it like 100 people, each with 5 measurements like height, weight, age, etc. I'm testing your understanding of the ledoitwolf estimator's properties. We'll compare it to the standard way of calculating covariance. This statement means that the ledoitwolf method always guarantees a mathematically valid covariance matrix. It's a crucial property for many statistical analyses. This claims that the ledoitwolf method is faster than the standard approach. Let's see if that's true. This statement says that ledoitwolf is especially useful when I have far fewer samples than features. This is a common scenario in many real-world datasets. This asks if ledoitwolf makes specific assumptions about how the data is distributed, e.g., following a bell curve. I'm using Sklearn, a popular Python library for machine learning, and specifically its ledoit_wolf function. This function calculates the ledoitwolf covariance estimator, a technique I'll explain further. I'm comparing two ways to estimate a covariance matrix: the standard sample covariance and the ledoitwolf estimator. The sample covariance is a simple calculation, but it can be unreliable, especially when you have many more features than samples. I'm working with a dataset containing 100 data points, samples, and 5 characteristics, features, for each data point. This specific dataset size is relevant because it helps me illustrate how the sample covariance can fail in higher dimensions, unlike the more robust ledoitwolf estimator. I need to determine which statements correctly describe the ledoitwolf estimator's behavior and advantages over the traditional sample covariance. Let's analyze them individually. This statement focuses on the crucial property of positive semi-definiteness. A positive semi-definite matrix ensures that all its eigenvalues are non-negative. This is critical because covariance matrices must satisfy this condition to be valid. The ledoitwolf estimator guarantees this positive semi-definiteness, unlike the sample covariance that can fail in high-dimensional datasets. Here, I'm testing if ledoitwolf is faster than calculating the basic sample covariance. It isn't, actually. Because of extra computation for shrinkage, it's more expensive. This is where ledoitwolf shines. When the number of features is far greater than the number of samples, a high-dimensional scenario, the sample covariance often becomes unreliable. The ledoitwolf estimator is specifically designed to work well in these situations. This statement explores whether ledoitwolf makes any assumptions about how the data is distributed. It doesn't, it's distribution agnostic, handling any data without specific distributional requirements. This quiz focuses on the ledoitwolf covariance estimator, a method used in statistics to estimate covariance matrices, especially useful when dealing with high-dimensional data. I'll explain its properties and how it compares to the standard sample covariance. We are given a dataset, 100 data points, each described by 5 characteristics. We'll use the ledoitwolf method to estimate the covariance matrix, and then compare it to the typical way of calculating covariance. I'm going to explain what to look out for in the following statements. This statement claims that the ledoitwolf method is faster. That's incorrect. The ledoitwolf method adds extra calculations for shrinkage, making it slower than calculating the sample covariance directly. This statement highlights a key advantage of the ledoitwolf estimator. When you have many more characteristics than data points, the standard method becomes unreliable. The ledoitwolf method is designed to handle this high-dimensional scenario effectively. It produces more reliable results. This statement says the ledoitwolf method requires a certain type of data. Nope. The ledoitwolf estimator is a non-parametric method. It doesn't make assumptions about your data's distribution. This statement is about a critical property of a covariance matrix, called positive semi-definiteness. This is a mathematical condition that ensures that the covariance matrix is well behaved. Ledoitwolf guarantees this positive semi-definite property. This is important because it makes the method more robust and reliable. This part isn't directly related to the core question about the ledoitwolf estimator but could be relevant for exploring the data visually before applying the covariance estimator. This simply refers to the number of data points in our dataset. This is needed for understanding the problem context of high-dimensional data, as this affects the suitability of the different covariance estimators. This quiz challenges you to test your knowledge of the ledoitwolf covariance estimator, a technique used in statistics to estimate covariance matrices, especially when dealing with datasets where the number of features is larger than the number of samples. I'll explain how it compares to the standard sample covariance method. Imagine a dataset. This dataset has 100 individual data points, samples, and each data point has 5 different characteristics or measurements, features. For example, imagine I'm studying houses. Each house is a sample, and features might be price, size, number of bedrooms, etc. This is a special method used to calculate the covariance matrix of a dataset. A covariance matrix shows how much different features in the data are related to each other. The ledoitwolf method is particularly useful when you have more features than samples, which is a common problem called high dimensionality. The standard method often fails in these scenarios. This is a table that shows the relationships between the different features in your dataset. Each entry in the table shows how much 2 features change together. A large value means the 2 features are strongly related. A small value or 0 means there is weak or no relationship. The ledoitwolf estimator helps us get a better, more reliable estimate of this table, especially in high-dimensional data. This is the core question. I am presenting you with a problem involving 100 samples and 5 features. I am asking you to use your knowledge of the ledoitwolf estimator to compare its properties to the standard sample covariance method, and to select which statements about the ledoitwolf estimator are accurate. We'll analyze each statement individually. This statement means that the covariance matrix calculated using the ledoitwolf method will always be a valid covariance matrix, a mathematical property that ensures meaningful results. This statement checks if the ledoitwolf method is faster than the basic sample covariance calculation. This statement assesses if the ledoitwolf method excels in situations with many features and relatively fewer samples. This probes whether the ledoitwolf method makes specific assumptions about how the data is distributed. For example, if it assumes a normal or Gaussian distribution. I'm comparing the ledoitwolf covariance estimator with the standard sample covariance. I'll focus on their strengths and weaknesses, especially when you have many more features than samples. That's a common challenge in data analysis. It's like comparing two tools to build the same thing. I'm working with a dataset that has 100 samples and only 5 features. This is a relatively small dataset, but it's a good starting point to understand the differences between these two covariance estimators. Think of samples as individual data points and features as different characteristics you're measuring. I'm using Sklearn, a popular Python library, and specifically its ledoit_wolf function. This function calculates the ledoitwolf covariance matrix, a special type of covariance matrix designed to address issues of the standard sample covariance, particularly with high-dimensional data. The sample covariance is the standard way to estimate a covariance matrix. It's simple to calculate, but it can be unreliable when you have a lot of features compared to samples, high dimensionality. Think of it as a basic tool. It works well in simple scenarios but can struggle with more complex ones. This question is about identifying the correct properties of the ledoitwolf estimator. It's a multiple-choice question that challenges my knowledge of this specific estimator's behavior. Let's see if I can ace this. This simply refers to the data that I'm feeding into both the sample covariance calculation and the ledoitwolf estimator. It's my starting point for this comparison.